In particle physics, a gauge boson is a force carrier, a particle with integer spin that carries any of the fundamental interactions of nature, commonly called forces. The elementary particles that we associate with matter, quarks and leptons, interact with each other by the exchange of these gauge bosons. For example, the average person normally only considers photons when they are thinking about light, but photons are also bosons that carry the electromagnetic force. If you were to look at the quantum level at the space between two repelling magnets, you would see the atoms of these magnets absorbing and emitting photons. As photons are to the electromagnetic force, gluons carry out the strong nuclear force. If you were to look at the nucleus of an atom, the positively charged protons should push each other away, as similar charges repel. But here, they don't. If this was the case, then the protons would never be able to form atoms and there would be no life. But this isn't the case thanks to gluons. By exchanging and emitting gluons, protons and neutrons undergo this strong nuclear force. It is a force with a short radius, but is roughly 137 times stronger than electromagnetism. This force is what keeps the nucleus of the atoms together, and similarly keeps quarks glued together as well. The final types of gauge bosons are the W and Z bosons, collectively known as the weak bosons. Weak bosons are responsible for carrying out the weak nuclear force seen during radioactive decay. For example, if an atom wants to change one of its neutrons to a proton, a W boson allows this to happen. The W boson carries away a negative charge and some mass away from the neutron, turning it into a proton. The W boson then instantly splits into an antineutrino and an electron, and imparts the weak nuclear force on these particles, which kick the antineutrino and the electron away from the nucleus.